Dear students, welcome to the lecture series on the topic Engineering Graphics. Today we are going to discuss about projections of the planes. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. Now, today we are going to discuss about projections of the oblique plane which happens to be inclined with respect to both the reference planes, that is horizontal plane as well as the vertical plane. So here we have got a pentagonal lamina which is having edge equal to 30 millimeter, and this lamina rests on one of its corners on the vertical plane in such a way that the surface of this lamina makes an angle of 30 degree with respect to the vertical plane. Now, since the surface of the lamina, it is inclined at an angle of 30 degree with respect to the vertical plane. So, to begin with, we are going to assume that this lamina will be parallel to, or it will be contained by the vertical plane. And here, one of the corners of this lamina, it is resting onto the vertical plane. So, this lamina will be contained by the vertical plane. So, to begin with, this lamina being contained by the vertical plane, so it is parallel to the vertical plane. So its projection onto the vertical plane, that is the front view projections of this lamina, they will be projected as true shape projections of this lamina onto the vertical plane. Whereas if we are going to look at this lamina from the top side, so we are going to view the edge view projections of this particular lamina onto the horizontal plane on the XY reference line. So we are going to obtain the true shape projections of this lamina above the XY reference line onto the vertical plane projections over here. Whereas the edge view projections of this lamina will be obtained onto the XY reference line. Now we are also provided with the information that the perpendicular bisector of the edge passing through the corner on which the lamina is resting, so this is further inclined with respect to horizontal plane at an angle of 45 degree. So here we have got the vertex D of this pentagonal lamina resting into the vertical plane. So from the vertex D, if we are going to join the midpoint of the opposite edge, that is the edge AB over there, that is this particular line which is going to be obtained by virtue of joining the vertex D which is contained by VP and the opposite edge AB midpoint. So this particular line, it is further inclined with respect to horizontal plane at an angle of 45 degree. So we are required to evaluate the front view and top view orthographic projections of this oblique lamina. So let us evaluate the orientation of the lamina which will be obtained onto the vertical plane as a true shape to begin with. Now if we draw the pentagonal lamina into this orientation and then we incline this lamina with respect to vertical plane either this way or this way. So the lamina will be resting into the vertical plane either at this corner or at this corner. But in this case, once we join this corner with the midpoint of the opposite edge, so we are going to get an inclined edge over here either this way or this way, which is inappropriate. We should be getting the vertex D joined with the midpoint of the edge AB in such a way that this edge, it should be either parallel to HP or it should be either parallel to VP. So it is neither parallel to HP nor parallel to VP over here. So this orientation is not correct. So the correct orientation will be this one. So here we can see this is the edge AB, then C and then D and E over here. So this is the vertex D. So if we incline the pentagonal lamina with respect to vertical plane in this way, so now this corner will be resting onto the vertical plane over here. And now this line which is going to be joined by this vertex D which is contained by the vertical plane with the midpoint of the opposite edge over here. So this line now happens to be parallel to the horizontal plane. So this way, even though this will be an apparent length, but still it is parallel to the horizontal plane. So that is why this is the appropriate orientation of this pentagonal lamina. So here we are provided with the apparent length of this shortest distance between the vertex and the midpoint of the opposite edge. And now we have been provided with the fact that the true length of this perpendicular bisector of the edge passing through the corner on which lamina rests on the vertical plane, this is inclined at an angle of 45. So here, now once we obtain the apparent length of the shortest distance between the point D, which happens to lie in the vertical plane, and this is the midpoint of the edge AB over here. So this is the apparent length. So what we are going to do here, the angle theta has been provided to us. That is the true length of this distance is inclined at an angle of 45 degree with respect to the horizontal plane. So using the principles of the rotation of the line, we are going to work out the angle of inclination of this apparent length with respect to the horizontal plane. So once the angle alpha is evaluated, so we will be able to transfer the apparent length projections of this lamina with respect to angle alpha with respect to the horizontal plane. Now let us proceed with the construction of the orthographic projections of this particular pentagonal lamina. So we know that this lamina happens to be contained by the vertical plane. So onto the vertical plane, that is in the front view projections, we are able to obtain the true shape of this lamina. So A dash, B dash, C dash, D dash and E dash. So this is the true shape of the lamina, and pentagon has been drawn with an edge of 30 millimeter. And now we know that ultimately we are required to determine this distance. So this is the true length of this distance over here. That is the distance between vertex D dash, which will be lying ultimately in the vertical plane, and this midpoint of the edge AB over here. So this is the perpendicular bisector of the edge AB, and it passes through the vertex D dash over here. So this is the true length of this distance. This midpoint will be named S dash as it is located onto the edge AB over here, right? So S dash is the midpoint of the front view projection A dash, B dash corresponding to the edge AB of this pentagonal lamina. So once we have obtained the true shape projections of this lamina, now we have to look at this lamina from the top. So as we look at this lamina from the top, so the edge view projections of this lamina will be obtained onto the XY reference line. So A dash, B dash points, they will be projected as AB, E dash, C dash points, they will be projected as E and C, and D dash point will be projected over here as point D. So this way, the edge view of this pentagonal lamina has been obtained into the XY reference line over here, or into the horizontal plane. Now we know that the surface of the lamina, it makes an angle of 30 degree with respect to the vertical plane. So this edge view needs to be reoriented or rotated at an angle of 30 degree with respect to the vertical plane. So this angle of inclination of the surface of the lamina with respect to vertical plane will be 30 degree, and we have to redraw this particular edge view at the orientation of 30 degree with respect to the vertical plane. Now the distance between D and EC, this distance will be translated over here. Similarly, the distance between EC and AB, it will be translated over here. So now the edge view, that is the top view projections of the lamina, which happens to be inclined with respect to VP at an angle of 30 degree, they have been obtained. Now the corresponding front view projections of this inclined lamina, which is having one of its corners, that is vertex D, located in the vertical plane. So the front view projections of this lamina need to be obtained. So the corresponding projections we are going to obtain when we draw the intersection points corresponding to the vertical projectors drawn from the plan projection points and the horizontal projectors which are drawn from the elevation projection points. So now we can see, once we draw the vertical projection in the upward direction from the point A1, now we have to extend this vertical projector in such a way that it should be intersecting with the horizontal projector which has been drawn from the point A dash. So this intersection provides us with the location of the point A1 dash. Similarly, B1 dash point can be located by virtue of the intersection of vertical projector drawn through B1 and horizontal projector drawn through point B dash over here. Similarly, we are able to obtain the points C1 dash and E1 dash over here. So we can check C1 dash point in the elevation view has been obtained by virtue of intersection of the vertical projector drawn through the point C1 and horizontal projector drawn through the point C dash over here. Similarly, E1 dash point in the front view projection has been obtained by virtue of the intersection of the vertical projection line which has been drawn through the point E1 and the horizontal projector line which has been drawn through the point E dash over here. And finally, D1 dash point, it has been obtained by virtue of intersection of the vertical projector line which has been drawn through the point D1 and horizontal projector line which has been drawn through the point D dash over here. So now the front view elevation projections corresponding to this pentagonal lamina which happens to be inclined with respect to HP, they have been obtained. Similarly, point S1 dash has also been obtained over here. Now we know that since this lamina, it happens to be inclined with respect to the vertical plane, so because of this inclination of this lamina with respect to the vertical plane, we are able to obtain this projection, that is D1 dash and S1 dash, as an apparent length projection over here. So this distance happens to be an apparent length, and now we say that this apparent length, because it is parallel to the horizontal plane, so in the top view we are able to obtain the true length of this apparent length. Now we are going to locate the true length corresponding to this apparent length D1 dash S1 dash even in this top view projections. Why? Because this apparent length D1 dash S1 dash happens to be parallel to this horizontal plane. So in the top view projection, now you can see this length D1 S1 appears as a true length in the top view projection. So this true length of this line is obtained even in the top view projections, and even we had the true length of this line available with us in the front view projections as D dash and S dash over here. So now the information available with us, it is that the perpendicular bisector of the edge passing through this corner on which the lamina is resting onto the vertical plane, it is inclined at an angle of 45 degrees with respect to horizontal plane. So this is the point D. You can check. Point D is the point into which this lamina is resting onto the vertical plane. So now the true length, that is D1 S1 or D dash S dash, is inclined at an angle of 45 degrees with respect to the horizontal plane. So this angle will be called theta. So theta is the angle of inclination of the true length with respect to the horizontal plane. So now we can mark 2 points over here. One point we can mark as D21 over here, and second point we can mark as S2 dash over here. So we know that true length is represented by B11 or B21 over here. So here we have got the true length point as D21 dash, and this is the first point of this true length, which is S2 dash. So this distance we have marked equal to the distance D1 S1 or equal to the distance D dash S dash. Now we can see this perpendicular distance from the vertex to the midpoint of the line AB. So this true length is inclined at an angle of 45 degree with respect to HP. That is why we have named this angle as angle theta. But into this front view apparent shape projections, we have got this distance projected as an apparent length, and we are required to transfer this pentagonal front view apparent shape projections over here. So how that can be done? We have to evaluate angle alpha over here. So what is angle alpha? Angle alpha, it is the angle of inclination of this apparent length with respect to the horizontal plane. So how this angle alpha will be obtained? So using the principle of rotation of the line, we'll measure this d1 dash s1 dash, which is the apparent length of this perpendicular distance over here. So this is d1 dash to s1 dash distance. So now with s2 as center, we'll measure this distance and mark it over here onto this construction line, which is the locus line corresponding to the point d21 dash. So this is true length. Now we are going to mark the apparent length over here, so which will be shorter than the true length. So once we mark this apparent length over here, so we will find that the point d2 dash has been obtained over here. So the moment we mark this apparent length between this locus line and this point over here, that is s2 dash, so we are able to obtain the angle of inclination of this apparent length with respect to the horizontal plane. And we know that angle alpha will be greater than the angle theta, because the apparent angles, they are greater than or larger than the true angles of inclination. Now once we draw the horizontal locus line over here, so we will be able to evaluate the measurement of the angle alpha. So angle alpha is, it is the angle of inclination of this apparent length of the point which is going to be there in the vertical plane, that is d1 dash, and the second point is the midpoint of the edge AB over here. So angle of inclination of this apparent length has been obtained. So this is 48 degree. So now you see this pentagonal front view apparent shape projections, they have to be transferred such that these projections will be inclined now at an angle alpha is equal to 48 degree with respect to the horizontal plane, and onto this 48 degree orientation, this apparent length d1 dash s1 dash will be lying. That is, this is d2 dash, this is s2 dash. So now this figure has to be reoriented or redrawn or rotated in such a way that this line d1 dash s1 dash should be lying at an inclination of 48 degree with respect to the horizontal plane. So once again, using rectilinear distance method, we are going to transfer this figure from the current orientation to another orientation in which d1 dash s1 dash will be inclined at an angle of 48 degree with respect to the horizontal plane. So now this is the rectangle which has inscribed this particular pentagonal apparent shape projections. We know the measurements of this rectangular box that we have drawn over here, which is going to inscribe this particular pentagonal shape. Now we are going to draw this rectangular block in such a way that this will be the center edge over here, that is d2 dash and s2 dash, and we are going to get half of the rectangle on this side, half of the rectangle will be located onto the other side. And now we know these distances rectilinear. Measurement from this extreme edge will provide us with a1. Measurement of this distance from the other edge will provide us with b2 dash. Similarly, measurement of this distance and this distance above the base will provide us with the points c2 dash and e2 dash, and the center point has already provided us with the location of d2 dash. So if d2 dash is located here, so we will have c2 dash and e2 dash located over here, and a2 dash and b2 dash located over here. So this way, these guidelines using rectilinear distances, they have been located. Now we can see locations of a2 dash, b2 dash, c2 dash, d2 dash and e2 dash have been located into the front view projections using this guiding rectangular box over here. So using these guiding projector lines, we are able to locate and transfer different points corresponding to this apparent shape into a new orientation into which this vertical line D2 dash S2 dash, it happens to be inclined with respect to HP at an angle of 48 degree. Now, the front view projections of the oblique lamina, which happen to be inclined with respect to VP at an angle of 30 degree and which happens to be inclined with respect to horizontal plane at an angle of 48 degree have been obtained. So the front view projections of the oblique lamina have been obtained. Now the corresponding top view projections of this oblique lamina we are going to evaluate. Now in order to obtain the top view orthographic projections, we have drawn horizontal projectors through the points A1, B1, E1, C1 and D1 over here. Now wherever they are going to meet with the vertical projectors drawn through A2 dash, B2 dash, C2 dash, D2 dash and E2 dash, we are going to obtain the positions of the points A2, B2, C2, D2 and D2 into the top view projections over here. So here we can see A2 point has been obtained by virtue of obtaining the point of intersection of the vertical projector drawn through A2 dash and horizontal projector drawn through the point A1 over here. Similarly, the point B2 has been obtained in the top view projections by virtue of intersection of the vertical projector line drawn through the point B2 dash and the horizontal projector line drawn through the point B1 over here. Similarly, you have got C2 point obtained in the top view by virtue of intersection of the projectors. One projector we have drawn through the point C2 dash, so this is the vertical projector, and another projector we have drawn through the point C1, so this is the horizontal projector. Similarly, wherever this vertical projector drawn through the point D2 dash, it intersects with the horizontal projector drawn through the point D1. So this way we'll be able to locate the location of the point D2 in the top view projection. And finally E2, this point has been located into the top view projections by virtue of intersection of the vertical projector drawn through the point E2 dash and horizontal projector drawn through the point E1 over here. So this way all the 5 points corresponding to the oblique lamina in the top view they have been obtained, and once we join A2, B2, C2, D2 and E2, so we will be able to obtain the top view orthographic projections of the oblique lamina, which happens to be inclined with respect to VP at an angle of 30 degree and at an angle of 48 degree with respect to the horizontal plane. So this is all for today. So I hope that through this discussion you would have understood about the procedure. How do we proceed to evaluate the apparent shape front view and the top view projections of the oblique pentagonal lamina, which happens to be inclined with respect to both the reference planes, that is vertical plane and the horizontal plane. So we are going to continue with the discussion regarding few more illustrative cases of the orthographic projections of the oblique planes in the coming lectures as well. So thank you very much. Thanks a lot.